Going to cover RC circuits today. So basically, just an overview of what RC circuits are. Well, basically, RC circuits are, you can tell by its name, it's a circuit that contains a resistor and a capacitor. Okay, so the circuit typically looks something like this, where you have a battery, of course, and it is connected to a switch which can take shape either on this node, which we call A, or this node, which we call B. Now this switch is connected to a resistor and a capacitor, and then it comes back up to B like this, and this is connected to the battery, as you can see from here. Okay, so now if this switch is pressed upon A, you see that it makes a circuit through A to the battery and through the circuit in this loop like this, right? Now on the other hand, if it is connected to B, then you see it makes a loop like this. So of course you understand that depending on which direction your switch is connected towards, you can have a different circuit. So first of all, since this is an RC circuit, we understand that these RC circuits will have, notions of charging the capacitor and also discharging the capacitor. So therefore, first of all, we're going to look at the charging part, where we charge a capacitor using an RC circuit. Now, when you're charging a capacitor, this only takes place if you connect a battery to it, right? So because you have a battery and there is an EMF running through it, if you connect the switch to A over here, in that case you will have the battery connected to the capacitor, and the capacitor will start storing charge, right? So when the switch S over here is closed on A, the capacitor is charged through the resistor, and of course we will see that when the switch is turned or closed on B, the capacitor will discharge through the resistor. Okay, so now first of all, what we need to do is we need to consider the fact that if switch is turned on A, the capacitor is being charged. So in that case, we're going to take this circuit and sort of, for our understanding, replace it as though the switch is turned on A. So therefore it will just connect the circuit with the resistor and the capacitor as so. So this is the resistor, this is the capacitor, and this is the battery. Okay, and it is connected by a point in A. So now first what we have to do is, since we want to understand or sort of derive equations of charging a capacitor, that means I need to derive an equation for the charge in particular, and I want to see how charge is stored in an RC circuit. So in that case, I need to first apply the loop rule to this circuit, and we're going to consider the loop going clockwise, which means it's going to go in this direction, which is basically the direction of the EMF. So therefore we can write the loop rule in the following way. So let me write it down over here, which comes from this circuit, and the loop rule will basically give me the EMF first. So I'm going in the clockwise direction, so I encounter the EMF, which is in the positive direction, and then I encounter R. So therefore I'm going to get a minus IR because of the resistor, and the resistor basically gives you a potential drop, and therefore I have a minus. And then I will come towards the capacitor over here, and of course I know the capacitor will store charge, and therefore it takes away from the circuit, and hence it will also contribute to a potential drop, and therefore I will write it like this. But remember, V in terms of the capacitance is basically just Q by C, because we know Q equals to CV, right? So in that case, I come back again to the end of the loop, and therefore I will get 0, right? Now, what I need to do next is basically formulate this equation in terms of Q. So I already know that I have an expression for I, which is the current, as dQ by dt. So I can replace that in my equation above, and hence what I will get is dQ by dt times R minus Q by C equals to 0, right? So rearranging this, I will get R dQ by dt plus Q by C equals to zeta, which is a differential equation for charging the capacitor, right? So therefore now if I want to solve this equation, you will see that this is a differential equation with respect to Q, and therefore if I solve this, then I will get an expression for Q. And since this is a first order differential equation and not part of the syllabus, maybe I will not show exactly in depth how to solve it, but there is an excerpt on the book that you can look into. However, I will tell you what the solution is, and the solution is Q equals to C zeta times 1 minus e to the power of minus t by RC. Okay, and this is your solution for, again, charging a capacitor. Okay, so now from here you can also derive the expression for current using this expression for Q, because I already know that I equals to dq by dt. So what I have to do is just derive this expression of Q with respect to time, and what you will get is zeta times divided by R times e to the power of minus t by RC. Okay, now remember, all of this is basically for charging a capacitor. Now a couple of things I can note from these expressions is that a capacitor that is being charged initially acts like ordinary connecting wire relative to the changing current. But after a long time, it acts like a broken wire. Now, what does that mean? Now, you see, whenever I have an expression of the current looking like this, it will work normally when we are considering t is arbitrary, right? But let's say that I now take a long time, meaning t goes higher and higher and higher and higher, right? In that case, you will see that as this goes higher, since this is on an exponential that is negative, it means that you're scaling I as t goes to higher t, as decreasing, right? Which means that since you have the expression of I to look like this, so e to the power of minus, right? So this is 1 by e to the power of t by RC. So of course, if you increase t, this overall expression will increase, and if you go to higher and higher and higher t, you see that this exponential will get higher and higher, and since this is in the denominator, it will overall scale this whole expression down. So in that case, as you go to longer t, as in longer time, you will see that the current will start to decrease and decrease and decrease, and eventually give you some graph. If you plot it where you have I against time, right, you will see that eventually it will just dip down and start to decrease until it is an asymptote with I equals to 0. So it is almost 0, but not really, right? Because of course the reason why this is an asymptote is because we don't have any expressions for the exponentials going to 0. So therefore this is not exactly at 0 per se, but you will have very small I if t goes to higher t, right? As you can see from here. And now the reasoning for that is, after some time, if the capacitor is fully charged, it will take away and store all the charges, right? In that case, you will have very less current flowing through the current. So it makes sense. Now this maximum value over here is of course when this expression is initial, which means t is at 0, right? Which means that the exponential will go to 1, and therefore this is at I equals to zeta by R, which is basically the amplitude of this expression. Okay, so now this is what I have as an expression for the current, and the reason why I say it acts like a broken wire after a long time, because you understand that the current is decreasing, so therefore at some point you will have current to be almost negligible, which would mean that it is as if that the wire is broken and there is no current flowing through it. So we can see that clearly from the expression. Now the next thing is we can also find the potential difference from these expressions, which we denote as Vc, and this is given by Qc, as we already know, and therefore we have the expression for Q, which is given here, and dividing it by C just gives you zeta times 1 minus e to the power of minus t by Rc. Okay, so all of these expressions are, remember, for when we have a charging capacitor. Okay, so now I want to explain a little bit about what this expression, or basically this constant term, is, which is denoted by Rc. So this Rc, the product of the resistance and the capacitor, which basically comes up in all expressions over here, is denoted as the time constant, which we denote with tau. And the reason why this is important is because you see this expression essentially scales all the variables, right? It scales how your Q is, it scales how your I is, and it also scales how your Vc is, the potential difference, right? So therefore this is called the capacitive time constant. So maybe I'll write that as the capacitive time constant, right? And it is denoted by Rc, and therefore now you can sort of replace all Rc notations with tau, and therefore now your expressions of Q from here just simply becomes C zeta 1 minus e to the power of minus t by tau. Your I, which is the current, which is given over here, now also becomes zeta by R e to the power of minus t by tau, and also Vc, also in terms of the capacitive time constant, becomes zeta 1 minus e to the power of minus t by tau. Okay, and the reasoning why this is really important over here, because you see when tau is Rc, which is equal to the time, meaning you are at the time constant, you see you get a sort of cutoff stage. That means it gives you a certain number, right? Because you see when tau is actually equal to t, you get a 1 over here. That means that now your QIVC will be scaled by the exponential, and particularly Q will then become C zeta 1 minus e to the power of minus 1, which is a number because now this is scaled by the exponential, and it will be 0.63 C zeta. And so this is sort of like a threshold, okay, which basically gives you a sort of number. So in this case I can say it in words, which means that during the first time constant, meaning when you put t equals to tau, the charge has increased from 0 to 63% of its final value. So you see you have charge to be 63% of C zeta, right? So that is what it essentially means. Okay, so now the next thing that we will do is we will switch your switch to B, right? And this would mean that now your circuit will just become the resistor, the capacitor, and that's all, because you are no longer connected to the battery, right? So what this does is basically you have now the capacitor that is fully charged and it has a particular EMF and so on, and now you're connecting it to the circuit without the battery, and therefore the capacitor now starts to supply the EMF in the loop, and therefore this is something that we call the discharge loop, because if the capacitor is starting to contribute to the EMF, of course the capacitor will start discharging, right? So therefore we call this the discharge loop, where EMF from the battery over here you see is 0. Okay, so now we're going to do the same treatment as we did for the charging one, and we're going to consider a loop again in this direction, and we're going to plug in everything that we did so far for the current and all of that. And now since EMF is 0, this expression over here just boils down to R dq by dt plus q by c equals to 0. So this is the discharging equation. Okay, now the same thing we will do that we did earlier. We're going to solve this differential equation and we will get a solution which looks like the following. Okay, again this is for the discharging equation where Q naught is the initial expression for the capacitor. Of course I have V naught over here because this is Q naught, where V naught essentially is the potential difference that is equal to the EMF that we started with. Okay, so V naught over here is the original, or basically the initial V naught, which initially was zeta equals to V naught, right? So basically this is the initial EMF of the battery. So this is the charge that we start with. Basically Q naught is the initial charge, which is equal to what it was when the battery was connected, and then you disconnect the battery, so therefore this Q will start discharging and therefore it will decrease from the initial Q naught. Okay, so V naught is the initial V naught, which is equal to the EMF of the battery. Okay, so now from here I can also express my I, which is given as dq by dt, and dq by dt over here is just, again differentiating it with respect to t, and you will get minus Q naught by RC e to the power of minus t by RC. Okay, so basically this tells us that the current also decreases exponentially with time at a rate which is set by RC, because this scales by RC, which is called the time constant, like I already mentioned. Okay, and that is all for RC circuits. Pretty simple.